To the third perfect problem for Math 213. In this perfect problem, we're dealing with duals, or this idea of duality. So we first look at it in the context of a tessellation. So the basic idea here, as I said, the basic idea here is that if you have a tessellation like we do here, this looks like a tessellation with hexagons and triangles. Semi-regular tessellation, if you're getting fancy. You can create a new tessellation, and the way you do it is you put a point, which will later become a vertex, in the middle of every face that you have. So I'll try to do that relatively quickly here. Actually, I'm going to pause this so you don't have to watch me put dots in. All these dots here, and what I'm going to do with these dots, or soon to be vertices, is I'm going to connect them. But not just arbitrarily. I'm going to connect any two dots if the faces that define those dots or vertices share an edge. So for example, I'm going to draw a line from here to here. And the reason I'm going to do that is because this triangular face and this hexagonal face share this edge right here. But I'm not going to draw a line right here because this hexagon and this triangle do not share an edge. Like, what about that little point right there? No, that's a vertex, that's not an edge. So if I go through and do that, I'm going to end up with a whole bunch of edges. Wow, this is sloppy. Maybe I'll do that a little bit prettier, but again, I'll pause the video. Alright, I think I've connected most of these dots here. There's still a few more down here that I kind of left off so that you can kind of watch me put these together, I guess, if you want. At this point, you can call this good, or you can point out that really there should be another dot up here because there should be another triangle up here. So kind of this line should keep going up here. And similarly, this one should go straight up because there should be a triangle. And you can kind of continue the pattern if you feel like it. I don't think you have to. Actually, I know you don't have to. I'm the teacher. I can decide those kind of things. But if this is something you feel like doing, just so the pattern's a little prettier, go right ahead. But something you don't feel like doing, hey, no problem by me. And so you fill them all together and you get this pattern here. This thing does have a name. Floret, I think it's called, something to that effect. It's supposed to look like a flower. I don't know, whatever. You don't need to know all that. All you were supposed to do is sketch the dual of this design pictured, then sketch the dual of your answer. Oh my God, I want you to do that too. Okay. It'll turn out that the dual of a dual is just the original picture. And we can show that if we take all these shapes and kind of put dots in their centers. And it can be a little bit hard to put dots in their centers because we end up with some shapes that are irregular. But for example, in the center of all these guys, I could put these little dots. In the center of all these guys, I could put these dots, and so on. And what ends up happening if you connect dots that share, so this dot and this dot should get connected, right? Because the faces that define them, this face and this face, share this edge. So I should connect them. But wait a minute. What's going on here kind of looks like I'm just ending up with the exact same pattern that I already had. Right? All I'm doing is putting lines where there are already lines in black. I'm just tracing the black with blue, essentially. What I'm figuring out here as I make this picture, and I think I'm going to stop at some point, dual of my dual is just this original design, 3.3.3.3.6. Exclamation point. Maybe you're excited. Maybe you're not. It appears that the dual of a tessellations dual is just the tessellation. And that's true. Just by construction, the way you make those work out, that you always just kind of get the pattern back, which, I don't know, I think it's kind of cool. Anyways, moving on, more with duals. In 12.6, in our next section, we're going to look at three-dimensional shapes. They're called polyhedrons, or polyhedra, or I've heard polyhedral, whatever. There are a bunch of these polyhedron guys. It turns out that there's 5 that are really famous. They're called the Platonic Solids. They're the only ones that you can make out of regular polygons if you kind of put them together in such a way that all of the angles, and what do you mean by angles? Well, it's a little bit complex, are the same. And so you get this tetrahedron, this hexahedron, this octahedron, dodecahedron, and icosahedron. And what I'm asking you to do is find the dual of these shapes. And so how the hell do you find the dual of a shape Well, basically, what you're going to do is you're going to take each of these faces now, because we're three-dimensional, and you're going to put a point in the center of the faces, which is pretty hard to do. I don't even know which of these I should try to do it for. Maybe, okay, so I have this cube, and the front face has a center right about there. Maybe this is up front. And then on the back one, it's got a center right around there. And then on this one to the side, the center's right about there. And on this bottom one, the center's down there. And on this left one, the center's over there. And on this top one, the center's up here. And I have my 6 vertices. And now what I'm going to try to do is I'm going to connect those guys. Oh, these start to pop in and out if you stare at them long enough. Give me a headache. I'm going to connect these guys. But as it says up here, I'm only going to connect the vertices with an edge if those faces share an edge. So for example, this front face and this right face, which is this dot and this dot, those guys share an edge. They share this edge right there. So I'm going to connect this guy and this guy. And this right face and this back face share an edge. So I'm going to connect those guys. And this left face and this front face, oh, it's starting to pop in and out on me again. There we go. And then this left one and this back one all share an edge. Then each of these side ones kind of share an edge with this top guy up here. So I can sort of connect them all. And each of these side ones sort of share an edge with this bottom guy here. I'm missing one. Where's... Wait, 1, 2... Oh, back here. Jeez, this is hard to do. 3 dimensions, hard to draw on. Anyways, if I did that correctly, which I'm not convinced I did. 1, 2, 3... Yeah, I guess I did. Just looks weird over here, I think because I got sloppy. Looks like an octahedron. Let's try that again. Exclamation point. So what I'm going to do over here is I'm going to list the tessellation, and then I'm going to list the dual. And I know all of these, so I'll just kind of say what they are. I'll leave the proving up to you. The dual of this tetrahedron. Maybe I should draw it. It's going to be really hard to draw it. I don't know if it'll benefit anybody. The dual of the tetrahedron. Turns out it's just a tetrahedron, which is kind of cool. You can almost picture it. Like if you picture this as a pyramid, it's an upside down pyramid. Because you're going to take the middle of all these faces that connect to this top point, and you're going to connect all of those. And that's going to become your new base. But then the base, the center of that, is going to become your new vertex, and you're going to end up with a tetrahedron kind of upside down in there. The hexahedron appears to have an octahedron as its dual. This guy appears to be the dual of this guy. And the same logic works that the dual of the octahedron is the hexahedron. You can find that in 2 ways. You can sort of connect faces here. Maybe I need a different color. Maybe I should just leave this out altogether. I don't know. There's the front face, then there's one back there, then there's one here, and there's one back here. And if I connect all of those guys, well, okay. Connect those guys. And then up here I have this front face, this back face, and this front face. And if I connect all of those guys, I end up with, I did that horribly, the ugliest looking cube you've ever seen. But this looks like a hexahedron or a cube. And it's true. The dual of the octahedron is a hexahedron. Another way you get there is up here we kind of concluded that it looks like a dual of a dual is just the tessellation. So it would kind of follow that the dual of a dual here would be that polyhedron. And it turns out that's true. The dual of the hexahedron is the octahedron, and the dual of that dual should just be the hexahedron, and sure enough it is. And then over here, because I did not want people to try to draw this, I showed you a picture showing that the dual of an icosahedron is a dodecahedron. And so using that same logic, oh, maybe this should have been back in blue, the dual of the dual being the original shape, then the dual of a dodecahedron, you might guess, is the icosahedron. And sure enough, it is. Just like the dual of the icosahedron is the dodecahedron, the dual of the Good enough. So here's the answers. I'll leave it up to you to prove them. I don't know how the hell you guys are going to prove these. Trying to draw pictures or something, which will be really hard. But maybe with more time, you can do them a little bit more, a little prettier than these. But I'm going to go ahead and end my solutions right here.